Good. Okay. Hello, everyone. Nice to meet you guys again. I think in the session we have around 50 people. I think there will be more and more people join. Okay. Now it's time. First of all, let me give a very brief self introduction to you guys. My name is Brown. I'm from China. I work for Automobile, formerly Continental Automotive. Today, I'm your host. I'm happy to have you in the session. And now, let me introduce our session. This session will present the PIBuster, exploiting a common misconfiguration in CCS EV chargers, which is a new attack vector targeting Qualcomm HomePlug GreenPHY modems in EV chargers and vehicles. The research identifies a misconfiguration DOS attacks affecting many deployed chargers. Joining us on stage to present is Masao Sakai, PhD student in the System Security Lab at the University of Oxford. Masao's research focuses on EV charging infrastructure security and includes contributions from Sebastian Kuhner and Professor Ivan Martinovich from the University of Oxford. So let's welcome Marcel to the stage. Marcel, now it's your stage.
All right. Thank you everyone for coming to our talk. So I'm excited to share this work with you that we've done into the security of EV charging.
Sorry, Marcel, I have to interrupt you. Can you hear me?
Yeah.
Yeah. Before your beginning, I want to also give some words to our audiences. So, guys, if you want to ask some questions to Marcel, please raise your questions on your right top corner. There is one Q&A session. Please raise your questions in that section so that Marcel will answer you at the end of this session. Okay, that's all. Sorry, you can continue, Master.
Yeah. So this is some work we've done together with my colleagues. And so kind of to get into it, first of all, as a bit longer of an introduction, who am I? I'm a PhD student at the System Security Lab at the University of Oxford. And as Bron mentioned, I research EV charging. That's what my entire PhD is on. And in my spare time, I also kind of keep looking into EV security. So part of the work that we talk about here today is a mixture of stuff that kind of we've done as part of publishable research, and then also some stuff we've looked at afterwards. So just some quick views or disclaimers. The views expressed in this talk are not those of our university necessarily. And though I don't think I need to explain this to professional people, but if you work with EV chargers, there is a very high danger risk because of the high voltages and the potentially high powers inside. So in our work, we never really actually open up any of the high voltage sections. We do not touch the power lines. We only look at kind of communication systems. But yeah, if you look into this, stay safe. And additionally, of course, cars and chargers are very expensive. And I will be talking about a vulnerability which can potentially essentially break their ability to charge. So again, it's very important to be responsible with this. So what we will be talking about today is a variety of EV charging standards. So this talk covers together the CCS1, CCS2, and NECS connectors. Nowadays, this is because they all share an underlying common standard called ISO 15118. So what are these? At least modern Tesla does. Originally it didn't, but now they've moved over to the standard as well. So what this standard boils down to is when you plug your EV into the charger, there is something called basic signaling, which is basically a hot plug presence detection signal. And then it turns on something called power line communication, which will be the focus of really the rest of this talk. And this is a somewhat old technology you may be familiar with if you've used Ethernet over power line adapters in your house. It's exactly the same technology. It's just going over the charging cable now. and it transports Ethernet packets. And then on top of this, we have the vehicle-to-grid protocol, which is a complex IP stack that deals with everything from power delivery, timing, payment, all sorts of things you might want. And after all of this negotiation passes, you actually start to charge your battery. But yeah, for the purposes of this talk, we will just kind of be looking at the physical layer of the system. So we will be looking at the power line communication link. Just for a bit of history, CCS is an evolving standard. There's kind of an almost unofficial version of it, which has become also the de facto standard used by everyone, called DIN 70121 from back in 2010. And now the latest version of the standard or of the protocol released is from 2022. There have been a lot of improvements in features, a lot of improvements in kind of security design. One thing that has, however, not changed is that the HomePlug link is always the physical layer. So all data will always go through this power line communication system. This is why we found it so interesting to attack. And so we really kind of wanted to understand what is out there in terms of deployments, because of course things can, it's obviously different standard versions. And in addition, you can have many different kind of implementation subtleties. So to do this, we built an EV emulator box that you can see here. It plugs into the charging cable. It's again important to note that it's only connecting to some of the data pins of the connector. We never touched any of the actual power pins. And inside our box, we've just got a Raspberry Pi, one of these power line communication modems, and then a power bank to power it all. So essentially, it's exactly the same modem that you would actually have to find in all the other cars and chargers. So we went on a road trip to collect some data. And this meant we had to drive up to a charger, plug in via the charging cable, and then our box over the next 1 or 2 minutes basically does in quick succession many charging sessions with kind of different parameters, different protocol selection, just to see what the charger supports. At no point did we do any penetration testing. This was all just kind of benign charging sessions to see how the chargers really respond. You can see here a map of the locations we visited across the UK, Switzerland, Hungary, and Croatia. In total, up to 397 different CCS plugs. And this was a reasonably wide range of sources. So we have 26 different manufacturers, highways, small towns, all sorts of kind of different chargers. We saw devices that were manufactured back in 2013, and we did our study in 2024, and the newest device we found was manufactured in 2023. So first, just some quick things about the protocol support we found. As I mentioned, CCS has many different kind of versions with different security capabilities. So one of the things they introduced back in 2014 was TLS can optionally be used to protect the charging communications. As we see, basically no one currently uses it, at least not at the time of our study. It was 12% of chargers which actually had it enabled. And there's no real kind of correlation with the newer devices being better at this than the older ones. TLS certificates can be bought for a reasonably low price. So we just think that this is something that everyone operating charging stations should work towards to have TLS enabled. And we wonder if maybe there's some kind of difficulties with hardware security modules or other kind of similar business contract paperwork that come kind of on top of the technical difficulty of actually implementing it. Then we looked at protocol versions. So we have ISO 15118-2. This is also the standard variant from 2014. And we, in our study, saw 47% of chargers supporting it, which means 53% of chargers only support the one and only oldest version of the standard. Even though it is essentially the same protocol at the binary level, so it's almost, it should be a very easy implementation to kind of add this in as an additional feature. And so we can start kind of moving the industry forward and deprecating. But just for compatibility's sake, this is something we've kind of seen, and in a certain sense, we also kind of understand that because every vehicle supports it and every charger supports it, then this old version of the standard has kind of just become the secure de facto. Right, and now on to the part of the talk which is kind of most related to the rest of the research we did here, the modems themselves. So one of the things we can do is we can actually ask the charger what specific modem is inside of it. And it turns out every single charger has the QCA 7000 or the 7005 chip, both from Qualcomm. They are essentially the same chip with minimal differences. And we can also query out the firmware version. So our pie chart shows what's actually in use. We have a lot of stuff from 2013, 2015. This is, I guess, what the modules were just shipped with by default, and then it doesn't really get updated. Something specific we, for example, looked at is that my colleague Sebastian published a broken wire attack. It was disclosed in 2022, published in 2023. And no firmware we found in our study is actually newer than this. So even if it is possible to fix it just by a firmware update, it is currently not done. So let's understand what really are the implications of this. So for many purposes, you really can just think of these Qualcomm power line modules as essentially Wi-Fi chips. They have on one side an interface where they exchange Ethernet packets, and on the other side, they exchange these complicated wireless packet-looking waveforms. It's just that instead of an antenna, it's connected directly to some wires inside of the charging cable. So it's not strictly a wireless protocol, but it is still in the physical layer very, very similar. And everyone's using just these chips from Qualcomm. And unfortunately, we wanted to take a closer look into kind of what they can do, but they are somewhat secretive about it. So there's no real data sheet or firmware provided. You basically, as far as we understand, need to get an NDA or some other sort of business relation with Qualcomm to get documents. You can even see that they, for example, removed some of the firmware from one of their Git repos when it was accidentally posted, though it may be possible to recover it. There is, however, an open source utility which is actually released by Qualcomm, and it allows you to look at the modem configurations and also change them, and this is completely open source. Now, this exists because power line technology is also used, as I mentioned earlier, in your home. So when you buy these Ethernet power line adapters, you kind of need to configure them, and there are some vendor-provided tools when you buy one of these adapters, but you can also use the OpenPLC utils. And the technology we use in EV charging is essentially the same thing, so it's essentially the same chips, and therefore the same tools will just work with them fine. So looking through these tools, we could kind of understand a bit more about what these modems actually do. So they contain something called the parameter information block, or called the PIB, which is a proprietary format binary configuration file. It doesn't really have any internal metadata. It's just certain locations in the binary correspond to certain settings. And based on the source code of OpenPLC utils, we could figure out that some of them are, for example, the MAC address of the chip, a manufacturer, display string, the network membership key, which, to come back to my favorite analogy, because these chips are very similar logically to kind of Wi-Fi, the network membership key in this case is the pre-shared key. So a bunch of important settings, and some of them you actually legitimately need to change. For example, this network membership key. So to do that, you can send a special control packet to your own modem. It's just an Ethernet frame as well, just with some special field set. And you can ask to read or write your PIB configuration. And OpenPLC utils provides handily this little command where you provide the file name you want to write and the MAC address of your chip. And this is where we had the idea, what if we put in a MAC address that doesn't belong to our chip, but for example, if I am an EV, I have my own chip, and on the other side, the charger also has its own. So what if I put in the charger's MAC address? And well, yes, this works. So in this case, you have the management message. It goes to my PLC modem, which notices that it's not the intended destination, and it modulates it out into one of these HomePlug packets, and it goes through the charging cable into the remote device. So this means that an EV can edit the configuration of the Qualcomm modem inside of a charger, and the charger can do the same back to an EV. So this is what we dubbed the PIBuster attack. Now, this is quite serious because the PIB contains a lot of important settings, and a malicious configuration can easily break the device by essentially stopping it from turning on either the power line interface or the host interface. So it kind of just cuts itself off from the world. And without the communication chip, there is also no EV charging, at least no DC EV charging. So we did a bit of testing in our lab, and what we found is that it works, but only for some of the devices. Even though the firmware on them was always basically the same version, it was just stock unmodified firmware directly from Qualcomm. So how can devices behave differently if they're running the exact same code? Well, we already know that there is this configuration file on it. So we assume that there is actually a security bit somewhere inside of the PIB itself, which determines if you are allowed to overwrite it. This is fine until you realize that this file is approximately 10 kilobytes, and we are looking for what is presumably 1 bit with no documentation provided to us. So what we did to figure this out, we got a vulnerable PIB from one of our portable EV chargers and then a secure one from a development board, and we tried to compare the binaries. And they are very, very different, including in the file size, because they were not exactly the same firmware version, and the different firmware versions have slightly different PIB sizes as they keep adding new and new features with more and more configurations to the end. So the first thing we did was we truncated the files to the same size, and we put them onto the exact same modem, so now they were running on the exact same firmware, and yes, they still get different results. So for our test procedure here, we had a Raspberry Pi that was kind of acting as a controller, and then we had 2 power line modules, both connected to it over Ethernet. And the power line modules were then also connected to each other over kind of the power line interface with basically just some wires. And what this enabled us to do is we could put some sort of victim configuration onto one of our modems, get the 2 modems to pair to each other, and then remotely via the attacker modem see if we can read the configuration out. Now not through the privileged local interface, but through the power line interface. And then we can also do the same to execute a write command. So the next thing we then did is we started to try to narrow down which exact bit in this PIB is important. And to do that, we basically merged the two files by just taking the first half of one of them, the second half of the other, really hope that we are not kind of cutting over an important setting in the middle. And we ran this on the modem. And in this case, we found that the modem was secure, which meant that the security bit is in the second half. And then we did binary search to kind of move this cutoff point, and we narrowed down that the security bit is at the location of 1F8C, and it's just a single bit. If it's 0, then reading and writing is allowed, and if it's 1, then it is blocked. So with this further knowledge, we went on to kind of further investigate, is this actually turned on by default? As I said, some of our devices had it on, so maybe this is something that every EV charger manufacturer has just figured out, and it's all good. So by default, if you buy these modems stock, at least the ones we did, they did not have it set in development board form. And then if you have real chargers, well, maybe it's set. So we needed to go out into the wild. And much like we did with our previous measurement study of protocol versions, we now kind of did a PIB measurement study. And so instead of trying to write to the configuration, we would just try to read, because what we observed is when the security bit is set, not only does it block writing of the configuration, it also blocks reading of it. So if our read was blocked, then we just assume it is secure, because there is no way it would allow writing if it doesn't even allow reading. But if it allows reading, it might still have some special configuration where reading is allowed but not writing, which would actually make sense. So then we further check the security bit we identified. And in total, we, for this measurement, tested 69 chargers in California, and 41 of them allowed us to download the PIB, and 41 of those that allowed us to read it, based on our analysis, would also have allowed us to actually overwrite their configuration. So this is a pretty serious scale of impact. It means that anyone who can drive up to one of these vulnerable chargers can put a new configuration onto the powerline module, and if there are some certain bits set in that configuration, it will essentially break it. Now, there is one important thing to mention here, and it is the procedure called host booting. So the PLC chip has an external, or can have an external flash chip next to it, and in this case, the firmware and the PIB are both stored on the flash chip. And this is the configuration we are most familiar with from our lab. And in this case, if you manage to push a malicious PIB to it, it's kind of game over, because the device will keep booting from the flash chip. It will keep reading back the same configuration, and there's nothing you can do about it from the outside. However, there is also a thing called host booting, where you don't use flash, and instead, every time the chip powers on, you can push the firmware onto it directly from the host interface. And in this case, if you try to write to its configuration, it will actually save it into RAM and it will use it. But the next time you power cycle the chip, it has no persistence, and therefore it will download a new fresh setting straight from your kind of host system. So this is much more secure, but we can't easily tell how many chargers and vehicles actually use this. It is kind of our impression that if you buy your power line system as a module, so one of the modules, for example, is shown here, but many others are available, and you buy it as a kind of plug in and forget type of thing, then it will have its own flash chip. Whereas if the chip is an integral part of the PCB design, then likely the developers also took the time to set up host booting properly. You can also somewhat guess from the MAC addresses and the manufacturer device strings if it's actually using one of these well-known modules. And so it is our understanding that most of the chargers do not use host booting, but many of the vehicles actually do. So yeah, in this case, it's still somewhat vulnerable to an override, but at least the attacker cannot achieve any persistence. So with all of this information, we conducted our disclosure. We disclosed to Qualcomm, and in addition, we also talked to ASRG and Charin to spread information about this. So yeah, we sent off our email back in February of 2025, and Qualcomm responded that they are in fact treating this as a vulnerability, and that a new firmware will be released, which essentially removes the security bit entirely, and it will just be hard-coded to block it. So I'm not entirely sure if this is out yet, but if you're operating chargers, please look for the new firmware and install it. Right, so this is where we get into kind of the additional fun looking at these chips. We were interested what else is hiding inside them, because if we're operating without documentation, we really don't know what else they are capable of. So we started reverse engineering them. So the first thing we found is that they have an SPI interface towards the host system. I mentioned they communicate via Ethernet. For practical reasons, it's Ethernet frames, but they are going through an SPI link. And then on our development board, there is just the second chip, which is a dumb media converter between Ethernet and SPI. And then the second thing we have, of course, is the flash chip, because this is one of the flash booting devices, not a host booting one. And this is also an SPI flash chip, so two SPI interfaces so far. The logical step is to dump the firmware, or dump the flash, and to kind of have a look at the contents and see the firmware. So from OpenPLC utils, we know that the structure is an NVM chain. It's a doubly linked list consisting of headers and then data blocks. And in fact, the first with checksums and metadata that describe what's in each block. And in addition, there is a manifest block always at the start of the chain, which has nice build strings, dates, kind of a good description of what we're looking at. So we dumped the SPI flash chip, and we're expecting to find the firmware and the PIB, because these are the two things that need to be stored on the modem. In reality, right at the start of the flash chip, we found indeed an NVM chain, and it describes itself as a soft loader. And it also has a block describing the flash layout, which helped us figure out what else we are looking at. So then there is a firmware chain, which consists of a bunch of code modules, and then at the very end, a big firmware section. And within the firmware section, you have a second entire chain with a very short block of ARM code, and then a high entropy binary blob. And then we also found some space for custom modules, the PIB as we expected, some scratch space, and then a backup firmware, presumably if something gets corrupted during the update. So for the boot sequence, what we put together is that there is the soft loader, which is responsible for kind of loading the main firmware. Then it goes through all of these firmware code modules, and then it reaches the final stage. It jumps into this small firmware section, which is then responsible for decoding this high entropy blob, which is presumably some form of encrypted firmware. So we wanted to have a closer look at this to see if we can break the encryption. And yeah, so as I said, just from looking at the clear text portions, so the actual loading code, we know that we are dealing with an ARMv5 chip. And what it does is it jumps to this address in the high F address space, gives it basically the high entropy binary data, gets back something, and then it runs it. So this is clearly the decryption function. Now, ARM uses an entry point also in the same memory region, so this must be some on-chip bootloader code. So the next thing we do is we achieve code execution on the chip because the flash is unprotected, and there are no cryptographic signatures, so we are able to replace the soft loader with just some custom code, and we would like to essentially use this to dump the bootloader. Unfortunately, even though this is a communication chip, we are quite limited in I/O because even though it has a power line interface, all the code handling it is in the encrypted firmware, so we can't do anything with it. Similar problems apply to the Ethernet interface, to the GPIOs. The only I/O we've actually seen is how to read from SPI flash. So we can't actually write to the flash chip because we just haven't seen the kind of commands or the I/O system they use inside, but we have seen the ability to read. So we developed a simple little code which essentially takes the bootloader as data we would like to exfiltrate and uses it as the address for a flash read. And it's just issuing reads to these random addresses all around the flash chip, and the addresses themselves are the data we are trying to send out. And then we hooked up just an SPI listener, and we could see the packets coming out of the chip, which was slowly sending out our data. So with this, we got our hands on the bootloader, and we were able to reverse engineer a lot more of the I/O systems. So now we have the SPI to the host system, there's more details about the SPI to the flash system, as well as actual Ethernet drivers for other versions of this chip, which actually have the Ethernet hardware integrated. So the firmware apparently already has it. It's just the hardware that doesn't support it. Additionally, we found that the firmware is not actually encrypted. It is just compressed with LZMA. So for our next steps, we would like to kind of create C headers for the peripherals, decompile the firmware image, and understand the interface to the power line system. And we would hope that this will allow people to create a powerful research tool that essentially allows you to look at all the raw traffic on the PLC system in ways that were only possible with extremely expensive R&D tools or not at all so far. So this is the point where we asked ourselves, this is all very theoretical so far, what can we actually make this chip do? Could it run the classic video game Doom? So it has rather limited resources in terms of, we don't actually know how much RAM it has, but not much. It also has very limited amounts of flash space. Our only I/O is Ethernet, but there's no screen or mouse or anything because for all intents and purposes, again, this is just a communication chip, much like a Wi-Fi chip would be. There's also no operating system or floating point. So in short, yes, it essentially can, though with some limitations. So we've got here one of our development boards, and I just connected it to my computer over Ethernet. And as I plug in the power, the chip boots up, and it will start sending out UDP packets which contain the frames of the game. and you can send the keyboard and mouse input also via UDP to it. So the game itself is running fully on the chip. It's just the graphics or the user interface which I've outsourced to the computer. Right, so for the final parts, where does this all leave us? First of all, if you're operating any device with these power line chips in it, just set the security bit at the location that I've shown. This should at least prevent some of these configuration override attacks. And then additionally, keep updating the firmware on it, because this is a reasonably advanced device that I've shown. It has a complete ARM core in it, and all charging data is going through it. So potentially, if you start using plug and charge or any of these higher systems, it is transferring billing data. It is also transferring safety critical data about the voltage and the current that the car can actually handle. So it's important to make sure that, much like every other component in the EV charging system, this is also kept up to date and secure. And then also, from the entire community, we need more people looking into these chips and not just treating it as a thing you put on the board and assume it's fine. And we also hope that people can start publishing more about it, and also that the documentation becomes available so that the things don't have to be reverse engineered painfully, but people can properly take a look at it. And finally, very long term, I think the unfortunate conclusion is that we will need to find a new EV charging standard that moves away from using power line. In addition to these chips being vastly complex for what is essentially transferring low bandwidth digital data over a dedicated wire, the power line protocol also has a bunch of kind of weird quirks to it. So it is very, very similar to wireless protocols, which actually means that the charging cable can act as an antenna, and it will radiate out your wired communication signal for anyone in the neighborhood to actually pick up and sniff. And the same thing also goes backwards. My colleague Sebastian, this is what the broken wire attack was all about, showed that you can jam with very, very low amounts of power the power line communication. So you can wirelessly jam a wired channel, which is, again, something that shouldn't just really be possible. So yeah, in our opinion, long term, the understanding this is very difficult, given that it's been standardized into CCS. The industry should look at basically some new physical layer that moves away from PLC entirely. If you would like to look more into this, here are some links to our papers, as well as kind of the hardware we used and some of the document and the actual HomePlug standard, because while documentation about the chips themselves is not open, the actual HomePlug protocol itself is openly published. So yes, thank you for your attention, and then we can have a discussion.
Good. Can you hear me, Marcel?
Yep.
Good. First of all, thank you for your very informative and professional sharing. I learned a lot from your presentation. Thank you again. Okay, good. Now we have several minutes, so I would like to go to the Q&A session, and Marcel will try to answer your questions, guys. So if you have more questions, also encourage you to raise your questions in the Q&A session. Because we have time, so we can invite you to the stage to have an interaction. Let's see it. Okay, first of all, let me look at the Q&A sessions. Good, there are many questions. First of all, yes, the first one is from Alexander from Germany. Let's see. The question is there a chance to do a vehicle to grid or grid to vehicle exploit? How do you think of it, Marcel?
So the power line interface doesn't go towards the actual kind of backend systems. There are other protocols for that, and as far as I know, people are looking at it and are finding vulnerabilities. But that is not with these methods at least. The only thing we've kind of shown is the ability to hop between charger and car and charger. And specifically, you're hopping only to the communication modem. So you would then need to find further vulnerabilities inside of the chargers. It's probably running some Linux box or something like that to actually get onto the main system and then further out back into the network.
Okay, good. By the way, Marcel, if you in the following questions, if you want to have a interaction with the people who asked the question, please let me know. We can invite um, her or she to go to the stage. Okay, if you want. Okay,
Yeah, sure.
okay, okay. I think for this one, I think it's a little bit clear, so we can move to the next one. Let me say, okay, there is one very high voted one. Let me show it on the stage. Good. This one is from Jinika from India. Okay. This question is considering how critical public EV charging infrastructure is becoming, how realistic is it
Yeah. So basically, the only good thing about this attack in its current form is that you do need to go there to the charger, but it takes a few seconds essentially. Once you can make reasonably cheaply a box like we have, and from plugging in, it then takes a few seconds to actually flash the configuration you want onto the modem. So it's somewhat limited in huge impact currently, unless someone figures out some further kind of escalations. But from the charger manufacturer's point of view, actually fixing it is also a huge pain because, first of all, if you're not prepared, it's very hard to understand what's actually happened. All you see is that your power line module has kind of stopped working. And the only thing you can really do about that is replace the circuit board in person.
okay? Good. Let's move to the next one. We want to try our best to answer more questions. Thank you for your answer, Marcel. Good. The next one is from Parimana from UK. Okay, the same place as Oxford. Okay, how much do you think an
Um,
OEM should be? Sorry, Marcel. How much do you
yeah.
think an OEM should be worried about this imitation in chargers or investigate how this could affect their EVs?
Yeah, so as I mentioned, it's mostly the chargers which are vulnerable. Like it's very vulnerable just because of how host booting works. But I know that there are some cars out there which don't have it, and which equally have a flash chip, so you can actually achieve persistence. And then same thing applies with chargers. It basically breaks. You can break charging until you take it to the shop and replace the circuit board. So car OEMs, um, yeah, should also be worried and just make sure that you're applying the same good practices to keep yourself safe from this.
Yeah,
And the other thing is you kind of can assume that chargers in one way or another could have been tampered with. So as always, any data that's coming in through the charging cable must be strictly validated, as treated as a hostile system.
good. Also, I can't agree more with you, Marcel. So here, I want to add something. In China, especially because I'm in China. So from China, actually, many OEMs are worried about the chargers very much because it will directly affect the user experiences. Okay, because you will um, if you are the driver, you don't want to spend much time, and you don't want your you know the, your charger will be somehow exploit and break your car, so something like that. So people in China are very worried about this stuff, so they are very careful about this topic. That's why also in China there are very many researchers are try to improving the security of the charger and the grid, like you are doing, Matthew. So good. Okay, let's move on to the next one. Let me check. Good. It's also from my side. So let me also show it on stage. I want to have this opportunity uh, to ask. My question is, can you please explain it a little bit more on the attack path to manipulate the secure bit remotely? In your slide, Matthew, I saw you show us a secure bit.
Yes, so there is the security bit, and essentially once it's set, you can't actually write to the configuration anymore. And you can actually set it remotely. So if somebody wants to be a kind of good person, you can make a box which goes around to chargers and fixes it. Um, and this would technically work. It's not something we've done because, of course, there is always the chance that something just goes wrong. Um, but so it is technically possible to actually use the attack to patch the attack. And yeah, once it's set, theoretically it's safe. Though actually, one of my colleagues also found another attack which was presented at DEF CON, where you can send another management message and reset the modem back basically to delete the security bit. And this is also something which, as I understand, will be addressed in the new firmware. But at least for now, the best you can do is still just set your security bit and hope nobody does the second attack on it. And yeah, so this
Okay.
all of this goes through the charging interface. So all of the attacks we've talked about are things you do via the cable, via the host system, until you kind of send in the special bricking configuration. You will always be able to change the security settings as you wish.
Okay, understand better. Thank you, Marcel. Okay, guys, we have 3 minutes left. So we have another one question. Let me show it on stage, Matthew. Can you see it in the left side here? The
Yes.
question, Matthew. The question is from Stefan from Germany. And the question is, what would the charger manufacturers think if people went around fixing their chargers?
Well, legally speaking, I would say this is definitely still considered hacking. Um, I would assume the ones that noticed would and actually understood what's going on would probably be happy about it. And the others would probably never even notice, because if you don't, it's also kind of an unusual thing to actually pull the configuration from your from your PLC modem. It is again something you can do, but it's something you never have a reason to. Essentially, you only really want to write to it to change the NMK, which actually changes every single time you plug in a car. But yeah, still, I would say probably don't do it. It is illegal.
Yes. Okay. I think we are in time, so very happy to have you, Marcel, and also guys, thanks for your time and for your joining. So see you next time. So now we can end this session. Hopefully you have a very good time with us. See you guys.
Yeah, thank you everyone for coming.